step. So that's what we're doing now. So cool, cool, cool. We're starting on page 2. And question 19 says rewrite using rational exponents, and so does question number 20. So that pattern is we've got the, I'll put it as here. We've got X to the M and N. That's confusing. So let's use different letters. Here's A and here's B. And that's gonna relate to the fractional A over B. And then whenever that A over B reduces, of course, we reduce it. So this one is very basic. We've just got the fractional power. The 5 is in the bottom, the 2 is in the numerator. Right on. So then for 20, we see that we're going to do that several times, but we have to remember the EO rule. That's even, even, odd. And I say that right now because 19 had an odd index, so we didn't have to think about that at all. But in 20, we have an even index, and 2 is an even exponent, and so is 8. So those two values, if they come out as odd, will need absolute value. So looking at this, I'm going to have A to the 1, nope, I wrote 1, it should be 2 over 4. Then I'm going to have B to the 3 over 4, C to the 8 over 4, and D to the 5 over 4. So I've just given each one the denominator of 4. As I'm seeing this, I see that A and C will reduce. A is going to reduce just the fraction 1/2. So I'm going to have A to the 1/2 power. B stays as 3/4. C is going to simplify all the way to 2, which is an even, even, even. I don't need absolute value. And then D is going to simplify to 5 over 4. It doesn't simplify any further. So this is my final answer where I just simplified those fractional exponents. On 21 and 22, we're going backwards. So we're doing the same type of work. So thinking of this, I've got the bottom number goes in the pocket. So the number in the pocket for this one will be 2. And the numerator was 7. And so that's going to have a 7 here. So here I have written this with a radical. However, this is not simplified radical form. So I do think I want to simplify this. It's even odd, so I don't need to worry about even, even, odd. And I'm going to consider, okay, y to the 6th power times y to the 1st power, and then the square root of each of those. And I just did 6 and 1 because 6 is divisible by 2. That's going to give me y to the 3rd power, square root of y to the 1st power. So both of these answers are good. If it says simplest radical form, it does not say that. That's when we definitely need the second form. So in 22, we want to write that in a single radical, but we can't do that as it is now. We've got 3, 3, and 2 as the denominators. So let's get a common denominator of 6 for each of those. So I'm going to times by 2 over 2, 2 over 2, and this one 3 over 2. So that's going to give me x to the 4 over 6, y to the 2 times 4, 8 over 6, and then z to the 3 over 6. Now that they all have the same index, they can go together in the same radical. It's going to be, the radical is going to have the 6. We're going to have x to the 4, y to the 8, z to the 3rd power. Now, if I want to simplify this, I look to see, are any of these exponents higher than the index? And I see that the y to the 8th power is higher than the 6 as the index. So if I'm asked to put this in simplest radical form, I'm going to say y to the 6th power, because that's the one that's going to simplify out. And it's 6 plus 2, so y to the 2nd power. So then that y to the 6th power and the 6th root, that's going to come out as a y Then I have the sixth root of x to the fourth. Now it's just y to the second and z to the third power. And again, here I have the even, even, odd. So I'm going to put my absolute values there. I'm also going to box this original because I think that this might be the answer that's on the key of just that first simplified into a common radical. Okay, looking at 23 and 24, it says here, write in logarithmic form. Oh, so those are some problems that are in exponential form. So I'm going to write down that reminder to myself of the pattern formulas. Its base exponent is equal to answer. And that goes back and forth to the log form of log base answer equals exponent. And so we see that the base is always the base, right? It's log base and the base. It's just that the answer and the exponent are reversed in terms of where they are in the equation. So if I want to write it in log form, I'm going to start by writing the word log. The value for the base was 3. So next to the tail of g, I put 3. The answer is 2187. And the exponent was the number 7. So I've now put it in log form. With number 24, I'm going to do the same thing. So I see that the base is 1/4, the exponent is -3. The answer was 64. So that's going to change to log base 1/4 of 64 is equal to -3. Very cool. In 25 and 26, I can see that I'm doing the same thing, but I'm going the opposite direction. Now I'm going from log form into exponential form. So I remember that this is the exponent. The answer to a logarithm is an exponent. So when I start on those ones, I identify the base next to the g. On 25, it's 5. The exponent is -4. The answer is 1/625. In number 26, the base is 8, the exponent is 4, and the answer is 4096. So it's understanding this special pattern. All right, looks good so far. For 27 to 32, it uses the word evaluate. Evaluate is a word that means find the numerical value. So let's do that. Looking at 81, and I see that it is a fairly large number and it has a fractional exponent. So what I want to do here is rewrite 81 with a smaller value. So I know that I could write it with the exponent of 2, that'd be 9 to the second, but I want to go even smaller down to 3 to the 4th power. And then we've got the -3/4 power here. What we like about this is the rule is that we can multiply the power to a power. So that gives me 3 to the -12/4 power when I multiply them. Or you could cross cancel right away and just say that it's -3 power. So a negative answer, just a negative exponent means that the answer is in the denominator. So it's going to be 1/3 to the 3rd power. The exponent is now positive when I move it to the denominator to show that the answer to a negative exponent is in the denominator. And next I'll simplify that to 1/27. That's a number. So I've done this correctly. I found a numerical value. Awesome. So in 28, I'm going to use that same type of thinking because I see that it's a 1 number with a fractional exponent. So seeing that I've got 8 there, I can write 8 with a smaller power. Who knows what happened there? And I'm going to rewrite that as 2 to the 3rd power, and that is going to be to the 5/3 power. Again, I multiply these, and do we see a cross cancellation that's about to happen? Yes, we do. We end up getting 2 to the 5th power, which is awesome. We're just going to simplify that to the numerical value of 32. The answer to number 28 is the number 32. We found the value. On 29, let's see what that one looks like. Oh, 29 is different. So to help me with 29, I'm going to convert this to exponential form if I can't automatically tell. So this is equal to x. So the base is 1/5. The exponent is what I'm looking for, and it's equal to 25. So 1/5 as a fraction, I can tell that that is the same as 5 to the -1 power. And that's to the x power, and that's equal to 25. So I'm left with 5 to the -x power is equal to 25. Well, I'm going to write 25 as 5 to the 2nd power. Now we have a common base, so I can say, oh, the bases don't matter. I've got -x is equal to 2. So dividing by -1, I get x is equal to -2. I could have also just known, oh yeah, it's definitely going to be a negative because I went from a fraction to a whole number. Whenever I go between those two forms, a negative exponent happened, and 5 to the 2nd power is 25. So it's just -2. However, if you get stuck on something like that, here I've shown all my work to get the answer. All right, cool. Let's take a look at 30. Oh, we've done the same thing here. I went from a fraction to a whole number. So I already know my answer is going to be negative. Since I just did that work, the answer is negative, and it's 2 to what power is equal to 32? Well, we just did that a few seconds ago. It's 5. The answer is -5. If I wanted to show all my work for that, I would have written 1/2 to the x is equal to 32. Then it's 2 to the -x is equal to 32. And then it's 2 to the -x is equal to 2 to the 5th power. Because say logs answer the question, what power creates that solution? All right. Looking at 31, I see log here several times. Log, log, log. It's addition and then subtraction. So this is one of the combination rules. We've got to simplify these. In this case, I want to rewrite this as a single log that I can then evaluate. So I'm going to begin with the plus rule is to times. So that's log A plus log B is equal to single log A times B. So together, this is going to be log base 3 of 9 times 36. I don't know what that is, so I'm just going to write 9 times 36 minus log base 3 of 4. So you see, I'm just doing one step at a time. Next, I've got the subtraction. So that's going to be the same rule. And instead of log A times B, it's going to be log A divided by B. So that's going to change to a single log where I'm going to have these parts dividing each other. So still log base 3. The denominator is 4, and the numerator is 9 times 36. I feel good about this because I can now divide the part in the numerator that is divisible by 4. 36 is divisible by 4 and gives me the answer 9. So this is going to simplify to log base 3 of 9 times 9, which is 81. Log base 3 of 81. Now I can evaluate this. 3 to what power is 81? What's the answer for the exponent on 3 that generates the answer of 31? 4. The final answer to this long problem is the number 4. Very cool. All right, let's take a look at 32. Oh, sweet. 32 is going to be a lot faster because there's just one log rule here. It's the subtraction rule, which means I'm just going to divide the two values together. So this stays as log base 2 of 20 divided by 5, which is log base 2 of 4. The answer to that, 2 to what power is 4? 2 to what exponent gives me the answer of 4? The answer is 2 to the second power. And we're finished with that one. As I look back, we've now finished page 2. Let's begin on page 3. Oh, yes. So in page 3, we've got where did they go? We've got just a couple more properties of logarithms. We are condensing again. No expanding, huh? Okay. So I've got 33 here. So I won't need to evaluate, and I can tell I won't need to evaluate because I have variables which haven't been defined. Sure. So here I have a different rule. I have a 3 outside, and so that's going to be when I have log base x, and we had a here, and that pops up to become log base of x to the a power. So that a becomes an exponent. So whenever we see that, that's the thing that we have to take care of. First, this is going to be log base 5 of x to the 3rd power plus log base 5 of y. Now we can use that plus rule. That's going to change these two to multiplication. It's still log base 5, and it's x to the 3rd y. Final answer, I multiplied them together. It's a single logarithm. Looks like we're going to do similar work in 34. All right, so I'm looking for the exponent rule. I have to start there, and I see the 4 and the 2. I'm just going to capture the 2 and the 4. I'm not capturing the signs with it. So great, I didn't even need to show a different step for that. That's fun. Now I'm going to do the addition rule. So that's going to be log, and it's going to be a times b to the 4th power minus log c to the 2nd. And now I'm reminded that the c is going to go into the denominator. So it's going to be a single log a b to the 4th power, c to the 2nd power in the denominator. Final answer. And we don't evaluate this because there's no values for A, B, and C. All right, cool. Now we're looking at some first semester stuff. It says factor completely. So we're factoring, factoring, factoring. As I begin, I see that there are some trinomials and some binomials. Do I see any polynomials? Yes, 40 and 42 have 4 terms. So each of these will have a different strategy. Take a look at number 35. 35 is a fast factoring example. Because it's x squared, I hope that we can factor this in just 2 steps. So I make my t-chart, I put b here and c here, right? AC is just 1 times c, so it's negative 63 and positive 2. I want numbers that will multiply to 63 and add to 2. When I think of 63, I think of 9 and 7. And so for this to add to 2, it needs to be a positive 2. I want the 9 to be positive and the 7 to be negative. So this simplifies to x plus 9 and x minus 7. Final answer. So fast factoring is our favorite. Now on 36. It is not fast factoring because I have 6a to the second power. So I'm going to do the same type of work. I'm going to put my b value here. It's 1. So I want the numbers to add to 1, but then 6 times 12 is negative 72. This is the AC. So I want two numbers that are really close together. They're 1 unit apart to multiply to 72. So that is going to be the numbers 9 times 8. And again, it looks like we want the 9 to be positive and the 8 to be negative. So I'm going to use these two numbers now to split the middle term. That's going to say 6a squared plus 9a minus 8a minus 12. So that 1a became two different terms. From here, we're going to draw our fence and split the equation in half. And we're going to factor out any GCFs. So in the first, I've got 6 and 9, and they both have a. So we're going to take out a 3a. 6 divided by 3 is 2a. Plus, the a's cancel here, so 9 divided by 3 is 3. Awesome. Now, on those last two terms, I see that it leads with a negative 8, so I'm going to take out a negative. And it's going to be negative 4 that I can divide both 8 and 12 by. And that's going to give me positive 2a and then positive 3. Awesome. The binomials need to match when we're using this factoring pattern, and they do. So when they match, I write the numbers out front together, 3a minus 4, and then 2a plus 3. This is our final factorization. I don't know why my a looks a little messy there. Let's see if I can make that better. Gorgeous. Now let's take a look at 37. Oh, this is a binomial. And I'm looking at the exponent, and that's an exponent of 2. So I'm going to factor this just the way I've been factoring the others. I'm going to make my t-chart. This is x squared plus 0x minus 81. This is a special factoring pattern called the difference of two squares. So I want the numbers to add to 0, so be the same number, but opposite signs, and then multiply to negative 81. Looks like 9's our favorite number today because this is 9 times negative 9. 9 times 9 is 81, and 9 minus 9 is 0. So this quickly factors to x plus 9, x minus 9. Right on. We're factoring, factoring, factoring. Okay, 39 is added again. We've got another 9 problem. This is the fast factoring. We can tell because it's x squared instead of 2x squared, 3x squared, 4x squared, or 6x squared. So I'm going to make my t-chart. Needs to multiply to 18 and add to negative 11. So I first think of 6 and 3, and that's only going to add to 9, so that's wrong. So then I've got 9 and 2, that's going to add to 11. But 9 and 2 add to positive 11. So in order to get positive 18 and negative 11, we need both of these to be negative. So this is x minus 2 and x minus 9 in any order. Okay, 40. As I look at this problem, I count up 1, 2, 3, 4 terms. That just means I don't have to make a chart. I just jump right into drawing the fence. Looking at these first two, 8 and 3 are relatively prime, but they both have x squared. So I'm going to divide by x squared. And that's going to leave me with 8x minus 3. Now in 40 and 15, I'm going to divide out a positive number because it starts with a positive. And I think I'm just going to take out a 5. That gives me 8x minus 3. Awesome. I love this. These two binomials match. This is x squared plus 5 and 8x minus 3. So these polynomials, they look kind of gnarly, but they factor pretty quickly because we don't have to make the chart. You're looking at 41. Okay, I'm looking at this one, and this one is a trinomial. I see that it starts with 10, which tells me that it's not going to be the fast factoring. I'm going to put negative 17 here, and 10 times negative 6, negative 60 here. Now, the first numbers I thought of with 17 and 60 were 12 and 5. However, I need the numbers to subtract. They need to multiply to a negative, so only one of those could be negative. So this combo doesn't work. So I think of 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10. Okay, so I'm looking for the combination where when I subtract them, oh, here it is. It's 3 minus 20. So I'm going to split the middle term to positive 3 minus 20 so that the 17 would be negative. So that's going to be 10x squared plus 3x minus 20x minus 6. Now we have 4 terms and we draw the fence. In these first 2 terms, 10 and 3, they just both have an x. They don't have any number in common, so the x goes to the outside. It's 10x plus 3. Now this third term is negative, so we're going to take out a negative. And it looks like I'm just going to be able to take out a 2. That'll be plus 3. Right on. So looking at these, the binomials match. I've done everything good so far. Haven't made a mistake yet. That's great. Got x minus 2 and 10x plus 3. Looking good. All right, so it looks like we got 42. Right on. 42 is a polynomial, 1, 2, 3, 4. Love these. I'm just going to start by drawing the fence. Taking out an x squared from the first 2. I've got x minus 4. And then taking out a minus 6. X, and that will switch to a minus 4. Right on. X squared minus 6. And x minus 4, final answer. So we've only got 1 more minute left, so we're going to stop here.